Swayam Prabha. Digital India. Educated India.
Any guesses? What is a heap? From your CS class, I don't mind the definition as well. Textbook definition of a heap. Dynamic memory allocation, that's right. So heap is where you would do your dynamic memory allocation, right? So you would have constants and you would have global variables which would get allocated here, right, inside this. This is a read-write segment in cat. Okay. So these are actual addresses. The 5563A44BB000 is an actual address. Okay. And it ends, it starts at that point and it ends at this point, and it has read-write permission. Okay. And useful trivia, what are these addresses aligned to? You know what alignment is, right? What are they divisible by? What is the factor? Maths karo chahiye to on textbook and tell me the answer. See, all of them have 3 zeros at the end. Yeah. So what does that mean? What is the alignment? You probably need to write it down and compute it. So when you say 3 zeros, so what is the value 0xFFF? What is this value is what I want to know. And then what is the value 1000? And there's a very interesting bit of trivia over here, and the relevance of a term that you must have heard in your first year and then forgotten about. So what is this number in decimal? What are these numbers in decimal? 4095 and 4096. What is 4096? 4K, right? What is 4K? Ever heard of paging? Page sizes are 4K, right? So these are aligned to 4K, right? So now you know that these are in distinct pages. These are multiples of pages. These are multiples of page size, right? But then that is not the trivia I was talking about. This one digit or hexadecimal digit is how many bits? 8 bits? Is this 8 bit? 4 bits. What was 4 bits called? Nibble. When did you learn about nibble? First year? It was utterly useless, right? But now you know that if you see a nibble as 0, it actually means that it is 16 byte aligned. And you'll learn later on in life that 16 byte alignments are very, very important. As in, it's one of those holy numbers which you'll come across time and again when you're doing like computer architecture, right? So this is where nibble comes in useful, and this is why I imagine, I don't know for a fact, I imagine that people must have actually coined the term nibble to say that, oh, the lower nibble is 0, which means it is 16 byte aligned, right? So now you can actually use the word nibble somewhere and actually find good use for it. Anyway, so back to this. This is a very useful view of the program because you can now see where your global variables are, right? These are the addresses where your global variables are. And now this is a program that has already terminated, so it is not very useful, correct? Now you want to see this in a program that is always running. So let's try and do that. Quickly write this program down. And this is a very long program, so I'll give you a full 5 minutes to write this down. So what am I doing in this program? I have 4 includes. Okay. Then I define a thread function called thr. All right, and all that the function does is sleeps for 500 seconds. Okay. Once you're done with this, I'll explain the main program, which is also very simple. So those who have done pthreads before can guess what is there in the main program. It just creates a thread and waits on that, waits on the thread. So this is pretty much what the program is. If you're done with the thread program, the program below is just this. It calls a pthread create and then a pthread join. The join basically makes sure that it keeps running, waiting for the child. Done? Return type for? Oh, so that is just a coding standard for formatting. So so because I contribute to glibc, so we have something called as a GNU coding standard, where we have the return type and whatever on one line, and then the function name, and then there's one space after that, and so it's basically what it does is it makes it easier for us to read code when we are like because there's probably like 20-30 of us across the world, right? Most of us don't even speak the same language, right? Writing the same set of code. So we want to make sure that at least there are no misunderstandings because of misalignment of code. So the coding standard kind of helps in that. It becomes like this uniform body of code where you don't have to suddenly wonder where the opening brace went. You know where it's going to be at all times.
Then what if I have a comment?
That's fine. Yeah. That's the language parser aspect of it, right? So if you have a comment in between, the language parser should be able to identify that this is a comment block, ignore it, move to the next line. Okay, all set? Typed? How do you compile this? GCC -o and pthread. You can say -pthread as well. L is not required. That's a special thing for pthread. Okay, compiles as well. All right, not done. Done, right? So let me just quickly build this. So I say GCC -o threads and then -pthread, okay, or -lp thread is also okay, but then GCC actually identifies -pthread. All right, and now my threads program can just run in a loop. It will just stay there. Okay. Now in the next tab, I am going to try and analyze the thread program. First thing I need to do is find out its process ID. Okay. So I say pgrep threads, right? That is the name of the program. So pgrep tells me that the process ID is 10272. So now I can say cat proc 10272 maps, and this is my map for a running process. Okay. Is it okay? Do you want to see the program again? Oh, so the first thing I do is pgrep threads. Okay. That gives me a process ID, and then I say cat proc the process ID and maps. What is the name of a program? Is it running? Are you sure? You're getting 2 IDs when you say pgrep threads, right? Pick the first one. Are you sure you have not invoked 2 processes? That's fine, pick the first one. Two in square brackets? Just two. What have you named it? Thread or threads? Thread. Okay, that's why. Then pick the bigger one, the second one. So P grep is short form for PS AUX and then grep, okay? Grep thread then gives me, there's threads and then there is thread D, which is a thread daemon, K thread D rather, which is a kernel process. You won't be able to read that, right? So you want your process. Got it? Okay, the second one. All right. So once you read this, now you can do something useful with it. So in this, now if you trap the program under a debugger and look at various variables, you'll find them within these address ranges. They're these actual address ranges. So you can even, since this is a user space process, you can actually try and modify variables and so on and so forth and see if there are any changes. Okay, so you can do some real interesting damage over here if you wanted to, right? But now what we want to do is we want to look at the map and try to figure out what is where, and try to kind of map our OS theory classes to this. Okay. So this is your first one, right? So now every object that is there has at least 3 parts, right? So there is one part which is read and execute. Can you guess what is read and execute? It's code, right? Your code, whatever code you write, is going to be readable and executable, but never writable. Okay, so you don't accidentally write into your code. So your code section, the pages that are mapped are always only readable and executable. Okay, all of your global variables will be read write. So RW dash. Okay, your constants will be R. Okay, and then there is one page without any permissions. We'll talk about that a little later. Okay. Then there is heap, where all the dynamic allocation happens, right? Wrong. So that is where a lot of the dynamic allocation happens. So there are 2 ways in which dynamic allocation happens, and it happens at different levels. So at the kernel level, there are 2 ways. One is in something called as the heap, which is this, okay, and then another way is something called as an anonymous map. Okay. Now if you look at this map, for example, this map is anonymous. It doesn't have any file backing it. Okay, these are called memory maps. Okay, so this memory map is anonymous, but it has read write permission. So this is a dynamically allocated memory. All right. So there are 2 system calls which do that. BRK system call helps you allocate in the heap. Okay, and then there's an mmap system call which helps you allocate in a memory map anywhere in between. Okay. So why do you need those 2? So have you heard of the malloc function? Right. So malloc function is in glibc. Okay, and it uses both. It uses heap as well as mmaps. Why would you want to use heap if you can use mmaps everywhere, or vice versa? So one property of the heap is that it can only grow downwards, right? So when you are allocating chunks in that, so that's what malloc essentially does. It allocates a chunk, it gives you an address for a chunk inside, and it returns that address to you, correct? Now the problem is that when a chunk is stuck in the middle, you free it, and if you want something larger than that, you need to grow. So you have what is called internal fragmentation. You must have heard that, right? So the heap is susceptible to internal fragmentation. Whatever you allocate over there is susceptible to internal fragmentation. mmap is not. Then why not always allocate using mmap? That's a solution, right? We can always allocate using mmap, but there is a problem there also. What is the address, the minimum address size for this, or minimum page size, allocation size? It has to be 1 page, correct? It has to be 1 full page. It cannot be anything smaller than that. So if I have to allocate 4 bytes with mmap, how much will I have to allocate? 4K. So 4,000 whatever bytes is wasted. That is called external fragmentation. So you must have seen that in OS class, right? So now you see it physically over here, right? So in malloc we have this heuristic where 128 bytes and above, for some cases we use mmap, 128 kilobytes, sorry, and anything lower we use the heap, and we do computations within the heap, right? And the other problem with mmap is that every time there is a syscall. To allocate also there is a system call, to free also there is a system call. Whereas with break, we can allocate at one shot and then we can choose small chunks in there and return, right? So that's one aspect of it. Now the second aspect goes to the threads part of it. So you wrote a multi-threaded program, right? And both of the threads are now running in parallel. They are currently executing, right? Now, what is the property of the thread? As in, what are the properties of threads? They have the same address space, correct? So both threads have this address space. Both threads have this view of memory. Okay, that's what you see it as. This is the thread's view of memory. Okay, which means, or does it mean, you tell me, that this is the stack for both threads? Do 2 threads share a stack? No, right? So this cannot be the stack. Or is it a stack for one of the 2 threads? That's more likely, right? So which is the other stack? So the other stack is something that is dynamically allocated. And the way to guess it, and this is an educated guess that you can use only on Linux, nowhere else, is that every stack has a guard page on top. Okay? A guard page. A guard page is a page that has no permissions. Okay? And the reason why you do that is if you have a stack overflow, the stack overflow should not overflow into the neighboring map. So now, for example, over here, you have one guard page and read write anonymous map. Once again, this, right? So now if this wasn't there, your stack would have overflowed into heap. So now imagine you could have caused a stack overflow, and if you can craft it correctly, you can overwrite a specific variable in the heap. And that is a very powerful way to, that's essentially a bug that can be exploited as a security hole, right? This is essentially how most security exploits are written today, right? So to protect against that, to protect against an underflow, you have a guard page. And with the guard page, I can identify that this is the stack for the second thread. Okay? And similarly, you have something called as multiple heaps. So in this, there would be another heap, I am guessing over here. This or the other one might be a heap, right? Because in glibc, you have one heap per thread. And you can, you can engineer multiple heaps depending on the number of threads, so that you don't have to lock between threads. So they are faster, right? So this is basically how you view your program in memory. Whether you look at it from a debugger, so when you're looking at it through a debugger, you're looking at only one part of it. This is a holistic view. This is what shows you the fact that your program is not alone. Your program has multiple libraries, your linker, loader, Then you have a stack. You have something called as a VDSO, which I have not talked about. It's a very interesting concept. Your heap and your thread stacks, all of them are in there. Your thread control block, you must have heard of, right? Your thread control block is nothing but the lower part of your stack or the higher part of your stack, your thread stack. So your thread stack has this structure at the bottom, which has thread information. That is a thread control block, right? So this is your view of a process. This is all the content that I had. What I'd like to hear from you is questions, if you have any, in relation to this content or in relation to careers in tool chains, systems programming. I've worked with people right across the board when it comes to system programming, and I have done multiple roles, so I can answer questions about those as well. How to bypass the? The guard page, you mean? That is the guard page of the stack. It's not just a bit, right? So, like for your stack, there's an implicit guard page which is implemented by the kernel. This guard page, you mean, right? So, so attacks are typically how they work is you have buffer overflows, right? Like you have a buffer of size n, and you try to keep going beyond n, right? Or you have an underflow where you go under, right? So the page as such, when you're going under, you will end up accessing something that has no access and then segfault without actually modifying anything. So as such, there is no way to get past it unless your increment sizes are more than the guard page size, okay, which is highly unlikely because your guard page is 4K, right? So if you have a guard page of 4K and if you try to bypass, imagine you would rarely have an array which is like 4K structures and you are going like ahead by 4K. So there's no real way to bypass that. So is it an example that you are looking at, or as in do you have an actual example that possibly does it? Oh, okay, all right, yeah. So no, there's no way to do that. That is the reason why it is engineered that way. So there are other classes of attacks which can be used to do these things. Like you have, so this is just plain stack overflow which modifies this thing. Then similarly, there would be buffer overflows which could modify adjacent memory areas, right? Then there is something called as, there was a very famous vulnerability called return to libc, where if you look at the way your function prologue and epilogue is set, your return address is pushed onto stack, so it is in memory, right? Now imagine you have the return address on stack over here. So this is your memory, right? So you have your return address over here, and then your local variables. Okay, if your local variable is an array that can override the return address, then I can actually put in the address to the function called system. There's a function called system in glibc which allows you to spawn different programs. So you can use it to spawn a shell, right? So I can just put system over here, right, and that will jump to the system function. And if I manage to set my registers or whatever the stack correctly, it can execute whatever the hell you want, right? The way they protected this was to introduce, so to make sure that all of the libc addresses have a 0 between them, so that the string processing terminates at that point. So there's return to libc as well. Then there's another concept called ROP gadgets, where you look at different snippets of assembly code and you try to jump between those. You basically reuse those snippets of assembly code. So stack overflow is just one way in which you can do it. And as technology evolves, we try to plug all of those one by one, like with guard pages, or there's something called as address space randomization. Like for example, your thread is running like this with these addresses, right? There was a time when the exact same addresses you would get at all times. So you knew which function was at which address from a statistical perspective, right? So with address space randomization, this kind of jumps about a bit. It jumps about enough that you cannot guess in any reasonable way that this function is going to be at this address, which is also a very powerful mechanism to defeat vulnerabilities. Then there are hardware vulnerabilities, but that's a different thing altogether. Have you heard of Spectre and Meltdown that happened earlier this year? Yeah. So that is like a class in itself, and it's fun to read those vulnerabilities. Anything else?
One question that I had in the afternoon was how do people open source make money?
So
I guess that so guys are a little shy, so
okay,
I'll ask on their behalf.
okay,
How does one look at a career in open source?
right.
One make enough money or whatever? How is the job applying?
So there are two aspects of it, right? How do businesses make money on open source, right? And then how do open source engineers make money, right? So open source businesses, most of them make money from, so there are two ways. One is the Red Hat model or the Linaro model, where we make money out of services, right? Like Red Hat makes money out of support. And it's not just like technical support, call center, it's not that sort of thing, right? I started in tech support in Red Hat, by the way. It's more of, I want feature X in this compiler, right? And I want it to be done yesterday, and somebody has to work on it. And consequently, somebody has to work on it so that somebody gets paid for it, right? Like for example, a bank which has a very performance sensitive trading system, and this is an actual example where I'm anonymizing bits, right? Where the hot code, as in the most performance sensitive code, is 5 instructions when it should have been 3 instructions. So somebody actually needs to tweak the compiler pass to make sure that those 5 instructions are, that sequence as such is recognized, and 3 instructions are generated instead of 5, right? So that's where our job opportunities come from, and those job opportunities are never going to die, right? Because we are looking for faster and faster, better and better performance as years go by. We have newer processors that come in, we have newer programming languages that come in, right? And everyone wants to be able to support that. So the second part is hardware manufacturers, where hardware manufacturers have their own compiler teams, have their own technical teams, and they cannot like develop and maintain their own tool chain at all times, because whatever you say, maintaining your own tool chain is a very expensive effort. It's an extremely expensive effort. It is the reason why Intel, though it has its own ICC compiler, it is fast trying to move towards LLVM. It is very, very involved in GCC development for that very reason, because they cannot do all of the maintenance. So what open source, the ecosystem essentially does is, it ends up dividing the maintenance cost between different companies, right? Nothing happens for free. In fact, if you look at the list of contributors in glibc and GCC, a huge bulk of them work for a company for that reason. They are maintaining glibc, they are maintaining binutils or GCC, parts of it, improving it for a company. It is never a hobby project, right? It starts as a hobby project, and it almost inevitably, because we have such less compiler engineers, it almost inevitably becomes a profession. And it is a very, very lucrative profession, I can tell you that as well. As in, you can think ML, AI and all of that, they're not nearly as lucrative as compilers is. So yeah, so money is the least of your issues if you're working in tool chains. Definitely if you're working in open source, money is the least of your issues, because open source projects in general are under maintained, and companies are always looking for people to hire to maintain them so that they look good to their customers. So there is like a full robust economy around it. Okay. Any other questions? Questions to this effect are also fine. Great. So hopefully this was helpful, and thank you for your time, and happy to be here.